Okay. Okay. How was the test? I mean, okay, right? Not too bad, right? When you shake your head, it means no, yes. Okay, you don't want to talk about it. All right. Okay. Okay. In fact, I think maybe we recap quite a bit. So, because it's just a lot of notation, so let's just think of whatever we have, x, y, z. They are discrete for the time being. And so...
Professor, can you just slide it down?
Oh, okay. So we have this, and we are using the density function or the probability mass function of x. And suppose we are looking for g of xy. You can think of just doing this. This is a double summation. You sum over small x, sum over small y. And then now you use the joint of xy. And even if you say, suppose you have the joint of three of them, let's say just this one. I think this question was brought up last lecture. So you can either use the original joint distribution of x, y, z, but now you basically have to sum over all possible x, all possible y, all possible z, and this. So the x corresponds to, this is the small x, all right, lowercase. But then this expression and these expressions are actually the same, because what you can do is you sum x first, and then sum y and z. Now we have this. Okay, but this x is a constant with respect to your inner sum, so you can have this. Okay, and then this is just the marginal of x. So in other words, whether your thinking is like this, or your thinking is like this, then it should give you the same answer. Now, of course, it depends on how you proceed in the problem. If you proceed the problem to, or you are asked to find this one first, then you already have this on hand. And so as a result, you can just apply this one directly. Now suppose you were not asked to give the marginal density function of x, but you are just asked right away for this. So you have a choice. A choice is just use this as it is, because the entire context is in three random variables. They are jointly distributed. And so you do this way. Or you go back and do it separately. You first find out this, and then use back this. So it doesn't really matter, all right? So as long as you do it right, it should give you the right thing. Now, if I were to change this to continuous, all right, so the only change is in the integration, okay? So you just change everything here. And of course, the integration always comes with a pair, the integral and the differential. And here you will have dx, dy, dz. So this is a triple integral. And so this would be a single integral. And so this is the dx is outside, and then you have the dy dz here. And so this would be the dx, and here that would be the dy dz. All right, so that is the respective change. I mentioned quite a number of times. I mean, it's just a nuisance to first recognize that it is a continuous or discrete. So if you're looking forward to more advanced module, we will get rid of all this by having somewhat a unified approach. All right. So this is this. And then another thing that probably would be to, let's talk about X discrete. And then this is the form that we use. Now this is not the only form, but of course, I think, I mean, only after I teach this module did I realize that it is something that we have been using, but we need to address. So some of you asked these questions. So you have x1 up to say xn, right? So this discrete random variable have n values, and then these are the corresponding probability. So if you are interested to compute the expectation of g of x, so the first thing I would suggest you to do, if you have a table on hand, so you just compute g of x, and so as a result, this is g of x1, and then this is g of xn. Okay, so one of the things that you usually do, g of x would be x squared. You compute the second moment, because this is the one step that you will calculate the variance. So if you were having this, then this is just this, especially if you have, I mean, in R, what we would do is we input it into a vector or a list, and then R is able to operate this function on the list to give you this list. All right, and then you enter another list, which is corresponding to this probability. And R allows you to multiply list times another list, but they do it by the corresponding positions. Or in Excel, you can just do it multiplying the right cell with the other cell, and then you cut and paste the function over. So, so you are doing this. So you basically multiply pk, g of xk, and then you sum. All right, so this is how you get it. If you have a table like this, and you were asked to do this, then you just create one more row, and this. All right. In the software, of course, in R, it would be you creating a new list, or you think of it as a vector, and then you do it. All right. Okay. Because we are going to have the similar thinking later on, this is your slide 570. We will be computing this. All right. Since I'm here, I may as well just do that. So it is a little bit not so straightforward. So what you do is you multiply this, and then this. Okay, and the next thing is you multiply this, and this. All right. So basically, for each entry, you go back to what are the corresponding x and y. You multiply the entry in this table with respect to where the x and y are. So you multiply the x and y, and then multiply the probability of the x and y in the entry, and then you sum over all of them. All right. So that is the procedures. Now again, if you are familiar with, so I can think of x as a list, and then y as another list, and then this is a table. So I have to define something like cross-multiplying the list, not just corresponding entries. So I think you guys are much better in this than I do. All right. So this is what we are going to do. And one of the main function G that we will keep visiting is the function multiplying the two arguments, x times y. Okay, because this is going to be giving us the covariance. Why are we interested in the covariance? Yes, because it is a measure of correlations. So here we are looking at this. Okay, when I end my lecture, I should have used this better word, but I was lost in my word. So this is like usually mentioned causation implies association. This is a more general situations, but the correlation that you are using at the moment is what we call Pearson linear correlations. So this is just one part of the association measuring. And then now the converse is not true. If the two variables are associated, doesn't mean one causes the other. Now, one example is the following, is the shoe size and the vocabulary of a language. Something like this, right? Spell like this. We often see in a child, the shoe size is related, associated with the vocabulary. The larger the shoe size is, the larger is the vocabulary of the child. But we can't say the shoe size caused the child to have a larger vocabulary, or the larger vocabulary caused the shoe size to become bigger. It is because it is what we call, this is called getting old. This is confounding. So these two things, the age actually causes the shoe size to get bigger, and the age is also causing the vocabulary of the language to become larger. So as a result, you can see these associations, but you don't have the causality. But causality is the ultimate aim of all science, or all engineering, or all knowledge, because we basically want to understand what causation is. So since I'm here, one of the things is I wanted to find out the cause of a disease. So usually this is the cause that we are interested. But we might be looking at many other factors like, say, age, genetic makeup, and all this. Now, what the usefulness of this part is, this is true. No association implies no causation. Okay, so this is what we call counter-positive implications, right? P implies Q is the same as negation Q implies negation P. So these two are equivalent. So, so if you find certain characteristics, say age, has no associations with the disease, then it has nothing to do. The age has nothing to do with the disease, so you don't need to chase after this particular characteristic. So no associations, sort of like helping us to screen out the things. But after you screen it, after you have the features that are associated with the disease, doesn't mean that the features causes the disease, all right? So you still need to continue your investigations. But this is where you screen out the thing. Now, for example, heart attack. The male is more prone to have heart attack than female. All right. So I think in the 1980s, when they do this large-scale aspirin health study, they do it on the male first, and also do it on the older male, 40 to 84 years old male. So that is the idea is to try to have a strong link of the association first before they look at this. Then, of course, after that, they understand the aspirin has the effect of thinning the blood, and so it will have a protective layer for heart attack. So this is what we will have. So if X and Y are independent, the covariance is 0. And so this is the same. The converse is not true. All right? And we have an example. And now we introduce a term called correlation coefficient. Now the good thing about correlation coefficient is that it is independent of the units of your measurement of X and Y. So this is it's an absolute number. It's nothing to do with your measurement. Whereas the covariance will be in the unit of X times the unit of Y. All right? And this is just nicely knocked out. As far as I know, I think the guy who actually introduced this is actually should be Francis Galton. Galton is the one who actually introduced regression and then scatter plot and other things, hereditary genetic study. But somehow the Carl Pearson, the older Pearson, hijacked that. All right, so now it's called Pearson's correlation coefficient. Now, another important thing is the correlation coefficient. Not only it is unitless, but it can be shown to always lie between -1 and 1. All right. So I will demonstrate a bit later the rho here, RHO, is measuring the linear relationship of the X and Y. Some detail, if X and Y are independent, then the rho XY equal to 0. So meaning that the correlation is 0 or uncorrelated. Okay, we'll call it uncorrelated. But if it is uncorrelated, it doesn't mean it is independent. Oh, okay, so I think I've mentioned it. There are two other statements. I think it would be nice to point it out. Let me call it D and E. If rho of XY equal to 1. Now this is a mathematical equal, means exactly equal to 1. Then Y is a linear function of X. All right, and B is positive. So it means that actually it's a straight line and the slope is positive. So that is why people call it positively correlated. And so it is a perfect linear relationship, all right? And E, if rho XY equal to -1, we also have the same linear relationship. But -1 means the overall values are basically on the second quadrant and the fourth quadrant. So the line has to be negative, the slope, all right? So this is it. Now, of course, this is a mathematical statement. It has to be exactly equal. If it is, say, 0.99, you can think of it as almost like a straight line, but it won't be a straight line, all right? Okay, I want to show you I want to emphasize the word linear here, all right? Okay, is it big enough for you guys at the back? Or you want it bigger? But your eyesight is much better. So, okay, I introduce a number of points. So, I wanted to introduce -1 and 1, and then I have 18 numbers in between. So, and it is uniform. Okay. So, my endpoint is -1. The other endpoint is 1. I want to specify how many points are there. So let's say I have just 50. All right? Okay, I missed out this. All right? And then my y has a very nice relationship with x, 1 minus x squared. So this is actually a circle. So it's the semicircle in the on top of the x-axis. So I have a bunch of 50 points, x and y now. So I plot it. And so you can see in every sense of the word, x and y are associated or should be correlated, because once you know x, you actually know y, right? So this is the perfect situations. But when I wanted to calculate the correlations, okay, so in R it's just COR. This is almost like 0, all right? Because the linear correlation is trying to measure the slope of a line that is trying to fit all the points here. So now, of course, we are not going to teach regression in this module, but we can basically mention it. So I think of y as my response, and then x as my predictor. So I'm trying to fit a line in the form of a plus bx to fit this 50 numbers. All right. So I'll let you have this. And now, of course, if you just type this, oh, I missed out the. Okay, so if I do that, this is giving you the line. I can actually plot the line, but this is not important. So the line that they try to fit, so that if you use a line to fit these 50 numbers, this is the best line, okay? This is what we call the least square line, the line that has the smallest least square error from the individual time points. And now, if you look at, so this is actually explaining why the correlation is so small, because basically the slope of this line is almost horizontal. And this is trying to illustrate the point that the correlation coefficient that we are measuring is trying to measure the linear trend of the numbers. So it would miss this, all right? So my point is, now that software is so easily used, I'm not familiar with Excel, but I think Excel can definitely do this. My advice is always plot the points. So because by plotting it, you actually know it. And then you also do the correlations. All right, and so if you use the correlations, it gives you a number. So you need a number summary as well as a picture summary. All right, and the number summary might be off, telling you it's almost 0. You might think that they are not associated, but when you do the plot, the pattern jump out from the plot. All right, now. Why do I need a number then? Of course, if I see a plot, but having a plot, I mean, you don't quite quantify the relationship, so a number might be helpful. Another thing is, this plot may also be visually deceiving to us, depending on the choice of the scale. All right, it's not the time or it's beyond the scope of this module to show it. We can show there are examples that it looks very clouding around here is because you use a very large scale, x and y. So as a result, everything is, this little bit. But if you use a smaller scale, then the cloud of points will be much bigger. So the visual effect depends on the choice of your scale here. So if I choose, say, minus 100 to 100 and 0 to 100, your visual impact would be slightly different, all right? So this is important to realize that that is why the correlation is only one of the measures to summarize the relationship of two variables. It doesn't tell you everything. Okay, so this is an example. We wanted to calculate the covariance here. All right. So to calculate the covariance, the first thing is to calculate expectation of x, y. Now, I think I showed you the table earlier. So what you do is you use 1/8 times this entry and times this entry. So you multiply 0, 0 times 8. Now, once you realize that if you have a 0, actually it would not enter into your calculations. So you basically only need to look at this 3 numbers. Is that okay? You basically only need to look at here because only here x and y are both positive, all right? But these are just little trick here and there to do the calculations. Nowadays, you are using software and you don't need to save this kind of calculations. So I think I would just skip this, all right? And then expectation of y minus x. So one way you can go about it is this is y. 0 minus 0 times 1/8. And this is 1 minus 0 times 2/8, and so on and so forth. So this is one way to go about it. All right? Another way to do it is that you recall expectation is linear. So you can think of expectation of y minus expectation of x. So if that is the case, then you can work out the marginal and then do the expectation of x here and do the expectation of y here. So these are just some numerical trick. And now, of course, to calculate the correlation coefficient, you already have the covariance. So the two ingredients that you need would be the variance of x and the variance of y. And in order to calculate the variance of x, you calculate the expectation of x squared, which is an important intermediate step, and also expectation of y squared in order to calculate expectation of the covariance of the variance of y. And here you are doing this, and so the first thing you need to do is fix x equal to 1. So you have this row, and now we are going to renormalize everything into 1. So that is where is the conditional probability mass function. So you are going to divide this row by 4/8, and so which will be 0, 1/4, 2/4, and then 1/4 here. And so after that, it would be just what we usually do. All right. So I'll just leave this out. All right. Okay. So this kind of things is a little bit tedious, but in this module there are two kind of problem. One kind is probability problem, and which can be very tricky, and also depending on your entry point. If you think along a certain way, it is rather obvious. But if you don't think along a certain way, then everything is very hazy. Here, but usually the problem is quite short. But this kind of problem, you know what you want to do, all right? Just do it, all right? So, yes?
Just for covariance of xy, could you also denote it with like sigma subscript x subscript y?
Yeah, this is where this module is using. I think especially Professor Chan is using sigma subscript x and y to denote the covariance. Okay, so since you asked about this, this is will be the covariance of xy. So if you have x and y are the same, this would be the covariance of xx. But we know that this is the variance of x, so this is this. All right. So these are the notations that people commonly use. All right. Okay, so the next example is a continuous version of what it is. So we just have to do it, all right? Except that we are now doing integration. So this is I think we have encountered this before. This is a square. Okay, the first thing is to notice this is a square because in order to do, especially let's say when you do the covariance here, you need to calculate the expectation of x and expectation of y. And sooner or later, you have to calculate the marginal of x and the marginal of y in some way or another. So you can't get away from it. So to calculate the marginal, you are basically integrating things over a vertical line. But then the vertical line, what kind of expression you are going to use, whether you should use this or you should use this, you have to graph the region carefully so that you know over a particular segment of your line that you're integrating, it is coming from here and then elsewhere would be 0. So you can't avoid it, all right? But this is nice because it is a square. Now, I think I wanted to make a point because I think nowadays many of you are using computer or you don't use paper and pencil that often now. But unless you have developed a very strong sense after a lot of practice or somehow you can see it, then I think it's still using paper and pencil would be helpful to really graph it. Or unless you have some software that would graph this region for you. For example, I think some symbolic software like Mathematica or Maple, you can just enter the boundaries and then they would plot the region for you. All right. So the best is still do a certain amount of this kind of work. I mean, something that I learned it because I don't, when I first learned computer, I don't do the hard work. So as a result, I have a hazy way of doing it. But when I really need to get it done, usually it doesn't do what I want to do. But now, of course, I can get around it. I don't need to do it. My student will do it for me. All right. So, especially if they are my supervisee. So the first thing I usually ask is, are you familiar with programming? All right, this is almost a requirement. I say, if you don't know how to program, I can't help you. All right, so you're on your own. Okay, so this is just integration. So we are calculating this first. So expectation. So we really need the joint here. All right, so here we are just integrating x first and then y later. So I will just skip this because I think it is instructive that you do it yourself, all right? And so the thing that you have to keep, especially here, okay, I think this is not a typo, but this is the sort of like the style of the person who is preparing this set of slides. X is equal to 0, and so x is equal to 1 is carried over here, all right? So it's just skipping x equal to the symbol here. But I would suggest you to write x equal to 1 here because especially after a while you might be substituting the wrong thing. You substitute the y instead of the x. So anyway, so I will have this number, and then okay, we also have to, okay, this slide is shorter, but it should have been a bit longer because this slide is referring back to an old example. So this has been worked out. So if you have to do it, then you need to do this part. All right. This is straightforward here. And so I will have this. All right. Well, this looks familiar. Yeah. I think the next tutorial, at least one of the answer is this. Yeah. It's a coincidence, I suppose. The conditional probability density function. Okay, part B is aiming at this. So as the preparations, I have to calculate the conditional density. Okay, so now this is just a matter of presentation. In mathematics, it's a little bit, people tend to make the presentation streamlined. So because this portion is actually only when we are doing this that we need to do this. But the presentation is actually presented this first, all right? It takes a little bit more paper if you write down this using the conditional density here. But at this point you don't know, then you have to, of course, work it out as before, all right? So anyway, so I think the details are just quite straightforward, and the Nike slogan, just do it, right? Okay, so maybe I think any questions up to now? Okay, then let's have 5 minutes break. Give you an extra 2 more minutes. So let's come back at 10:50. Okay, one of you pointed out a typo in the lecture notes. It is here in your example 8. All right, when we are computing the conditional expectation, this is this table is correct. So basically, what the slide is trying to do is 0 times 0, 1 times 1/4, 2 times a half, 3. So this should be a 0 here. All right, there's a typo. But of course, this typo doesn't affect the calculations. There is something like in our body. We might have mutation. I don't know whether we're subject to mutation of our genome very often. But certain mutation doesn't have any effect on us because it's not in the coding region, or even if it's in the coding region, because our functioning is in terms of the protein, and because of amino acid is redundant. So even if you have a change of your DNA level, it doesn't change the amino acid. And as a result, you still have the same protein. So it's something like this. There is a mistake, but the mistake doesn't, cause any other incidents. All right? So we are going to introduce common probability distributions. This is where the modeling is. We are assuming certain situations. I will explain the modeling because I think probably you have learned a number of them, but I think you learn it as a textbook. One of the things is I actually didn't do statistics. I'm more mathematics trained. Not that I wanted to boast, but because when I first learned statistics in my undergraduate day, it was introduced to us just as it is. Okay, the probability density function is like this, calculate the mean and all this. So there is no interpretation behind. So I guess that really turned me off, all right? So that is the only statistic module I have taken. Then in my graduate school, my supervisor said, if you want to teach, it might be better that you learn some statistics take some statistic courses so that when you in your career you can teach some statistics. I took my one graduate module in statistics, and then I was turned off. All right. So anyway, so that's all the statistic modules I have learned. But when I'm older, I started to do more statistics, especially since 2000. So much older. I work on computational biology, and that is where I get my hand wet in statistics. Now, one of the things that are in variables, random variables are basically classified into two classes. One is discrete, and then the other is continuous. All right? And then the discrete one is called nominal, and then the other is ordinal. All right? So the nominal can be Bernoulli random variable. All right? And then also the binomial. Okay, the binomial, geometric that you will learn, and then the negative binomial. All right, and uniform. So uniform can be on both sides. All right. And continuous, we will have some example. We will have uniform distribution again. We have exponential. All this integration by part is because you are dealing with exponential distribution. And then you also have a normal distribution. Normal distribution poses us a little bit of a problem because the distribution function, which is the integral of e to the power minus x squared over 2, you will see it maybe 1 or 2 lectures later. We can't integrate it in a closed form. What I meant is, suppose you integrate sine x, it is equal to minus cosine x. You have a formula for your integrand. But for the normal density function, you don't have one function that represents the integral of the antiderivative of the normal distribution. So that poses a little bit of mathematical problem. But if all you care is numerical value, then you can put in your numerical calculations. So this is this. Let me explain what is meant by nominal and what is ordinal. Nominal means it's just a way of labeling the thing. For example, 0 for female and 1 for male doesn't mean male is bigger than female. There is no value. There is no comparisons. Basically, it's just a matter of labeling. Now, this is very much used, especially in the older days. People try not to save the data in a string. So they usually code it first, and then so what they say is there is a code book in the Excel file. Usually the first sheet is the code, what are the variables, and then how you code them. So there is like a dictionary. And ordinal means 0, 1, 2, 3. 2 is actually bigger than 1. 1 is bigger than 0. So you have this sense, all right? Like our shoe size, how many people are in this room. So these are ordinal random variable. So when we go this, we will talk about this one at a time. But bear in mind, this is the situations. And then there is, I think in the slides, it does not say very clearly this. But everything is coming from the Bernoulli random variable. Okay, so these are more or less the family member. So the binomial, the geometric, and the negative binomial. They are family members of the Bernoulli. Okay, I will explain. Okay, if you Google it, Bernoulli is, I think now more like something like already 300 years. The family, they are still very influential, but at that time it produces a lot of engineer, mathematicians, and all this. But there are also a lot of this, family feel. The father is, one of them is called Jack Bernoulli, and then I think his son is Daniel, and then Jack has a brother who is smarter than he. So they have a lot of fight. The father and the uncle fight. Later, the uncle died. The father and the son also fight for prestige in mathematics. So if you read about this, it's even more interesting than you watch some of these Chinese TV drama. This is in the mathematics, not in the palace. All right. Okay, so we are going to talk about this, but a lot of these things are actually interlinked, but the way it is presented, or at least when you read the textbook, they are not linked very tightly. All right. Talking about this quotation, I don't know why he said that it's important questions of life, but Laplace is one of the renowned French mathematicians. There are 3 French mathematicians around his era, all start with L. Laplace, Legendre, and Lagrange. I was told Lagrange is actually Italian, but the French make him to be a French. So Lagrange is in fact Italian. So since he started with the L, may as well change him to a French mathematician. All right, and some others. You will hear about. Poisson. Poisson is another French mathematician, but closer to probably around maybe 100 years ago. All right. Now, if a veterinarian had to learn a different pattern for treating every different breed of dog, it might be impossible for an individual to learn enough to be able to treat dogs in general. Similarly, situations involving uncertainty and probability fall into certain broad classes, and we can use the same set of rules and principles for all situations within a class. We first look at some classes of discrete random variable that arises frequently in application. I don't understand why the reference to the dog. I mean, maybe the person who is preparing it is a dog lover, all right? So, okay, so this is what I was showing the tree, the different kind. The first thing is a discrete but a uniform distribution. Now, uniform distribution in the discrete case is actually your equally likely probability space. All right? So, if you remember, we flipped the coin once, either head or tail. I assign half and half to it. So, meaning that the outcome is equally likely, head and tail. If I flip the coin twice, so I have head, tail, tail, head, tail, tail. I have 4 outcomes. And again, I assigned equally likely situations to these 4 outcomes. So as a result, it's 1 quarter, 1 quarter, and 1 quarter. So the discrete uniform distribution is actually these situations. All right. So I have a number of points. I call it x1 up to xk. I have k points. And then equally likely. So I know the total probability has to be 1. So each one has to be given probability 1 over k. So the 1 over k is because I assume uniform, all right? Or in our previous jargon, it is equally likely. Everything else outside these k points, I assign value 0, all right? Okay, the mean, variance, and all this can be very easy. So this is the general formula, but of course we don't usually use this general formula. We can rework it out again. All right. All you need to do is to produce a table. Even if the number of values is large, then your table is just dot dot dot, right? So you don't need to have the write down the entire table because the pattern is very clear usually. All right. So an example. This example is like this. A light bulb is selected at random from a box that contains a 40-watt bulb, a 60-watt bulb, a 75-watt, a 100-watt. So we have 4 kinds. Each element of the sample space will be just 40, 60, 75, and 100. Occurs with probability 1 quarter. Now, the reason why this is occurring with probability 1 quarter is because of a jargon here. The jargon at random means there is no preference as to which bulb to choose. So as a result, all these 4 bulbs are equally likely to be chosen. So at random, usually we mean this way. All right. So the rest will be just simple. So example 3. When a die is tossed, each element of this occurs with probability 1/6. Now, either you specify the probability as 1/6, or 1/6 will come in naturally if you have one more qualifying word in front of the die saying that the die is fair. All right. Okay. I read somewhere you can't have an unfair coin. I don't know why. But then you can have an unfair die. I mean, you can load the die in some way so that, yeah. Okay. Now, if I know the mean without much calculations. I'm going to put equal weight at 1, 2, 3, 4, 5, 6. If you have a little bit of physics background, the mean is actually the center of gravity. The center of gravity at 1, 2, 3, 4, 5, if they are equally weighted, then it would be in the middle. It would be really in the center of 3 and 4, so which is 3.5. So you don't need to do any calculations. Now, of course, this is you need to do it for sigma square. All right, and it turned out to be 35/12. So this is the variance. So the standard deviation should be just take a square root. The variance is about 3 times, okay, but actually it is the standard deviation is square root of 3, roughly, and it would be 1.7 something, all right? So your center is about 3.5 plus or minus something like 1.7 on the left or on the right. Okay, okay. Okay, this is now maybe I'll just explain it. I think this is very simple for you guys. Now x equal to 1:6 means I have 6 number from 1 up to 6. Okay, REP stands for repeat. All right, repeat 1 6 6 times. All right, so this is the number that you're repeating, and then this is the number of times you repeat it. So you basically P is a vector or is a list. 1 6 1 6. There are 6 elements in there are 6 elements in the list, and this is 1 to 6. All right. So when you or you can key in x equal to this. Now for R, any vector has to be with label C first to tell them it is going to be a list. All right, or a vector. If you just type this in without the C, R will not be able to recognize it, all right? Now, R also do this kind of calculations. X is a list, P is also a list. So when you multiply a list, you multiply the corresponding entries of each list. And then, so it will return you back a list, all right? So if you, maybe I'll do it here. I think I can do this. So this is the probability P. I assign 1/6. All right, and I can let you have a look of P. P is like a list. All right, in this way, X is 1 to 6, and then I can let you see what is X. So X is this. So X times P will be a list of just multiplying the corresponding entry. So, but now I actually want to sum them. In R, you can use an up arrow and down arrow to get back to your last, and so I can sum it. Okay, so this is 3.5, all right? Okay, and now I want to calculate the variance. Okay, I have to give a name to this first. So this is the mean. I don't know whether you can use MEAN, because MEAN might be a command in R in itself. So I don't want to try. All right. So now I wanted to calculate this term, the expectation of x squared. So to calculate the expectation of x squared, I simply square this first and then multiply with this. So, and this will give me this, all right? So this is the expectation of x squared. And now I want to compute the variance, all right? So I can calculate this minus the mean square. And so this is 2.99, this number, all right? Okay, so this is just a command to print out the number. This is something that I'm not very good in. So yeah, how to organize the output in a way that later you can save it to somewhere else. Okay. Since you guys are computer science students, actually R can talk to MATLAB. So and talk to other things. And also you can import Excel file into the R. So you can actually do things in different platforms. Some of my students who is doing very heavy matrix calculation, like finding eigenvalues for very large matrix, something like 600 by 600, and then and do it for many times because we are doing simulations. So the student actually move it, interface between MATLAB and also R for doing this kind of things. So I have this. Now, of course, this is just the variance. If you are interested to calculate the standard deviations, is the square root, all right? So this will give you the standard deviation. So this is about 1.7 something, all right? Okay. So random variables arising from repeated trials. I wanted to add in a word here, independent repeated trials. The trial has to be independently conducted. Now, for example, you are flipping a coin 10 times. It means you flip a coin repeatedly for 10 times. But we have to flip the coin each 10 times rigorously. Because if you have a head first, and then you really flip it this way, you have a tail, and then you flip it this way, you get a head again. So this is not what we are thinking of. We really think of, we do it in an independent of what we have already obtained. All right? So the next few classes of random variable arose from the study of a mathematical model for repeated trials. Okay, so we only look at one trial first. Each trial results in whether a particular event occurs or does not. Occurrence of this event is called success, and non-occurrence called failure. All right, so we label one outcome of a trial, one particular trial, is a binary. This is what we call a binary outcome. So we either label it as 0 or 1, or we call certain thing as success and a failure. Okay, and so as a result, the probability of a success is denoted by P, and then the failure is Q. Q is equal to 1 minus P. And we repeat these trials independently. Okay, so Bernoulli trials. A Bernoulli trial is an event, is an experiment with two outcomes, one of which we consider as a success, and another is a failure. So this is just a way of labeling, all right? So this is just some, so this is the experiment. The actual experiment is flip a fair coin, and then if you get a head, you think of it as success. If you get a tail, you think of it as failure. Or you roll a fair die, which will have 6 outcomes, but we are only interested in one particular outcome, for example, 6, which is usually the number you need to when you play board game, especially when you need to start. And then a non-6, all right? Roll a 2 fair dice, a double 6, not a double 6, or 3 fair dice. If you play small and big, kind of a gambling situation, triple 6 would be of interest, and so on. Birth of a child. Here it says success is a girl, and then failure is a boy. And you can change it if you don't like it. You can, in your slide. I think about a year ago, I always try to say this. So for all my teaching career, I have no negative feedback. But last year, when I was referring to this, having a girl as a success, one of the student feedback was, I'm so disappointed with you. How can you say this? And I don't know, it's probably inferiority complex, maybe. So anyway, this is meant as a joke, all right? Don't take it too seriously. If you really don't like it, change it, all right? But you have to change the probability, all right? I don't think this is right. This is probably just made up. I think most of the time, as far as I know, the girls are born with a slightly higher probability than 0.5. All right? So I think it probably might vary from country to another, from country to country. So pick an outcome. So this is where the usefulness of this. I have a particular outcome or an event, not only just outcome. For example, when I roll a fair die, I'm interested in getting an even number. So I would take 2, 4, 5 and label it as 0. Label it as 1, success. And then the probability of success would be half. All right? So, so we should change the word here, pick an event in the experiment, and then whether the outcome that you have is in this event, or it is not an event. So the original thing is actually composite, but you can have a dichotomized classification. Either is what you want or what you don't want, all right? So the probability of success would be the probability of the event A, and then since this is the opposite, so it would be 1 minus probability of A. So such trials also called Bernoulli, the P here tells, track down the probability of success. So this P has a meaning, okay? Now, of course, this is to be understood. Most of us use this notation, but when you, maybe in your other modules, you might want to explain what this means. So the P is the probability of success. It's named after Jacob Bernoulli, one of the many prominent mathematicians in the Bernoulli family. So you can look at some gossip, here, all right? So, yeah. So actually it is such a, extraordinary family of eminent scientists and engineers. But on the other hand, sometimes competitions bring out the ugliness of humanity, all right? So, okay. So sometimes competition makes us successful or push the limit or to improve the society or the community, but sometimes it can destroy one another. Mathematically, a Bernoulli trial is modeled by a random variable as follows. So, okay, so it is a very simple kind. The way it is defined is in this way. Of course, we have different way of writing it. So one way would be just simple as this is. All right, or another way, I think the table take up less space, equal to P when x is equal to 1, 1 minus P when x is equal to 0, and 0 otherwise. All right, so we can write it this way. Okay, now to calculate the probability, the expected value, this is very simple. Sorry, I have to keep switching around. So if you calculate the expectation, this is 0. It would not contribute anything to it. This is equal to P. Now this is just a formula, but a better way to remember is for Bernoulli trial, the mean is the probability of success. All right. Okay, I think the other part, the variance of x, you can calculate this, but the answer is P times Q, or P times 1 minus P. Again, you can memorize it in this way. The probability of success times the probability of failure. All right? So that might be easier to sink in. All right. So we have this. Now a lot of people don't like to write it as P times Q because you have to tell people what Q is. All right. So, but it really a matter of whether you're used to it. Okay, now we are going to introduce a kind of a family. Something that I mentioned about is called a parameter. So in a way, the Bernoulli random variable is not completely specified until you specify the P, what the P is. All right, so there is a number, the number we call it a parameter. We have to specify this parameter or specify this P in order to completely specify the random variable. Okay, if you think of it as a table, the very simple table that I draw, if I do not tell you what the P is, then the table is, in a way, is only a mathematical table. It can't, it's not, being used in in real data. So, and we call this a parameter. Now, the last part of our module would be the interest in trying to know this parameter. Now, if I model it, then I assume some number that is there in the population. And how do I know it? Then I do sampling, okay? And then I have some estimate of this parameter. And then after the estimate, I may also want to make a decision whether this parameter is a certain value. So that would be hypothesis testing. And then I wanted to have a sort of like an interval where my parameter is likely to be inside. Then that would be our confidence interval. So the interest would be say something about the parameter. But this is more like statistic part. As I mentioned in my first lecture, the statistic is coming from a more inductive way. I want to guess my population from seeing a sample. Whereas probability is I assume the population is behaving a certain way, and I wanted to derive the property of the randomness later on. So suppose the density function or the probability mass functions depends on a quantity that can be assigned any one of a number of possible values. So the collection of possible values is called what we call a parameter space. So the parameter that is in this set, the space here, will be a legitimate parameter to use, with each different value determining a different probability distribution. This is crucial. One choice of the value will give you the actual probability distribution. Such a quantity will be called a parameter of the distribution. For example, P is the parameter for the Bernoulli distribution. The collection of all probability distributions for different values of this is called a family of probability distributions. So maybe this is a little bit, a bit repetitive, but the point is, if I change my P, then I will have a different random variable. And then as a result, I have a collections of all these random variables. Why do we call it a family? Because it is not even countable here, because P can be any number between 0 and 1. So this collection of random variable or distribution is not even finite. Okay, it's not even countably infinite. It is uncountable. Okay, so we have this. All right. So this is the form that we use. We call success as 1. We call failure as 0. So we go between 1 as success and then 0 as failure interchangeably. All right. Okay. This is playing the roulette. Okay. A gambler makes a sequence of $1 bets, betting each time on black at a roulette in Las Vegas. Now the roulette there are two versions of roulette. I mean, it's time to educate you guys. Okay, the European version of the roulette has only 37 numbers, ranging from 1 to 18 red, 1 to 18 in green, and then 1 0. So the American version has the same as the European version, but have one more slot, double 0. So as a result, it has 38 positions. So when you buy color, so say green, so you only have 18 out of 38 probability of winning. Whereas if you play in the European roulette, you have 18 out of 37. So the chance is slightly higher playing over there. All right. So so this is probability of winning. So this is definitely when you win, you think of it as success, or when you win, you think of it as 1. All right. A box contains 4 blue and 6 red balls. If a ball is chosen at random, random here now at random means uniformly likely, what is the probability that the blue ball is chosen? So again, there are 4 blue balls out of 10, so this is 4 out of 10 and 6 out of 10 and so on. Now this is where we now bring in your chapter 1 back here, because when we define a certain event of interest which we label as success, then we have to calculate the probability there. And so that is why we have the chapter 1. And this is simply counting. Okay. Now here we have the first member of the Bernoulli random variable family. Is called binomial. Binomial is using the Bernoulli trials to, let's motivate it first. If I roll a standard die or fair die 10 times, what is the number of times 6 turn up? So what I do is I roll my first time. I see whether it is 6 or not 6. If it is a 6, I register 1 there. And then I look at the second row, and if it is a 6, then I have a 1 here. If it is not a 6, I have a 0. So according to my 10 rows, I would have 10 numbers. Each number is either 1 or 0. So each number is actually coming from a Bernoulli trial corresponding to rolling this die, all right? But now I'm not interested in the actual order of getting 6 or non-6. All I'm interested is the number of 6 in 10 rows. So I add them all up in the list. So this is the total number of times 6 turn up, all right? So I'm basically adding up all these Bernoulli random trials 10 times, all right? So a student randomly, so this is another scenario. A student randomly guesses 5 multiple choice questions. What is the number of questions the student answer correct or guess correctly? So the probability of success of getting it right, because under the assumption of randomly guess, so it is 1/5, and then there are 5. Depending on how many options in each multiple choice questions. And he's repeating it 5 times, all right? So randomly pick a family of 4 kids. What is the number of girls amongst the kids? Now, again, here I use a table. It's not my idea. Don't complain in your student feedback. You think of a girl as a success, all right? And so basically, now you have 4 trials for this family. And then you want to count how many successes you have, all right? I have 2 successes, all right, out of 2, all right, okay. So we now consider a sequence of n Bernoulli random trials. Xi is tracking the outcome of the ith trial, okay? So as a result, x1 up to xn, they are either 0 or 1, and I'm adding them up. So I basically count how many 1s are there, all right? Or how many successes are there. So this is a binomial. Binomial is fixing the number of trials, all right, in a Bernoulli, in repeating, independently repetition of the Bernoulli trials. Okay, so maybe I'll stop here. So just to summarize, so the binomial will be fixed the number of trials, okay, and n here. And here I have a p, so as a result I have n and p in my parameter, choice of parameter. And now you can think of the Bernoulli is a special, okay. So the binomial is the number of trials is fixed, all right? And P is the inherited from here. The Bernoulli can be thought of as n equal to 1. So once you have the binomial, you can think of the Bernoulli is nothing but a binomial distribution, except that you only try it once. Okay, coming up is this. Geometric means we do not fix the number of trials. But what we do is we keep repeating it until we have the first success. All right. Okay, just to balance out about the gender case, in case you wanted to complain, my mother-in-law keep trying until, she wants to have a son. She tried 6 times and all failures, all right, in her mind, all right, okay, and then she finally give up, all right, so, okay, so success and failure is relative. I mean, my point is, to some, having a lot of girls is a success. My elder sister has 3 boys, and she really wants to have a daughter, and she also give up. All right. So anyway, so success and failure is relative. Now, negative binomial is actually the same as geometric. I have a goal in mind. I have our successes that I wanted to have. So I keep trying it until I get our successes. So the negative binomial is actually a more general case than the geometric. All right. So we will deliberate all this relationship when we get into there. So it would be good to not to see each distribution as its own entity, but see that they are actually coming from a related kind of a scenario. All right. Okay. So maybe I'll stop here.